This video cast is on Chapter 15, Chemical Equilibrium. Concept of equilibrium. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. As a system approaches equilibrium, both the forward and reverse reactions are occurring. As you can see here, this is a rate versus time graph, and the forward reaction is occurring at the same time as the reverse reaction. And when they meet, you are at what's called chemical equilibrium. At equilibrium, the forward and reverse reactions are proceeding at the same rate. Here in the beginning, they're not. But here, past this dashed line, we've achieved equilibrium and the rates are equal. Products are becoming reactants, and reactants are becoming products. Once equilibrium is achieved, the amount of each reactant and product remains constant. Notice past this dashed line, the same amount of NO2 and the same amount of N2O4 both exist. In a system at equilibrium, both the forward and reverse reactions are being carried out. As a result, we write the equation with a double arrow. Notice how the arrow not only goes from left to right, but also from right to left, because at the same time as the reactants are becoming products, some of the products are also becoming reactants. How much of this reactant is becoming product, and how much of this product is becoming reactant can be told to us by something called the equilibrium constant. The equilibrium constant can be found by taking the forward reactions rate law. Notice it's a small k sub f right here, meaning the rate constant in the forward direction. And looking at the reverse of the reaction's rate, notice this is a small k with a little r, meaning the reverse reaction rate constant, and solving for those rate constants. Because at equilibrium, the forward rate is equal to the reverse rate, and if you solve for kf and kr, it becomes kf small k with a little f, meaning the rate constant in the forward direction, divided by k small k with a little r, meaning the rate constant in reverse direction. We get what is known as the products divided by reactants. This is the equilibrium constant, and the kf over kr is renamed. It's renamed big or capital K, and many times a small letter is placed below it. This is EQ, meaning the equilibrium constant for this reaction. Notice the ratio of the rate constants is constant at that temperature, and the expression now is big K is equal to the forward rate constant divided by the reverse rate constant. This new capital K right here is what this chapter is all about. To generalize this expression, consider the reaction A plus B goes to C plus D. The equilibrium expression for this reaction would be, notice this is a big or capital K, a small c because the equilibrium constant is written in terms of concentrations. Notice the A, B, C, and D are all written in brackets, meaning they're molarities. And the small c, d, a, and b are the coefficients in front of the A, B, C, and D in the balanced chemical equation. Notice in the equilibrium constant now, you can just take the coefficients from the balanced chemical equation and use them as exponents. So what are the equilibrium expressions for these equilibria? If we were in class, I'd actually have you write the equilibrium expressions for them, and we'd find out that maybe this isn't quite the time to throw in these first two reactions. We'll come back to some examples in the next video cast and later on in the chapter. Because pressure is proportional to the concentration for gases in a closed system, the equilibrium expression can also be written in terms of pressures. Notice now it is still a large K, except it's a small p down below here, meaning that the equilibrium constant is written in terms of pressures. These would be the pressure of the product C and product D raised to the power of their coefficients, divided by the pressures of reactant A and B raised to the power of their coefficients. There's a relationship mathematically between Kc and K sub p. From the ideal gas law, we can make that mathematical relationship. Rearranging PV equals nRT and solving for pressure, it equals nRT divided by V. Plugging this into the expression for K sub p for each substance, the relationship between Kc and Kp becomes K sub p is equal to Kc times RT to the delta N, where triangle N is equal to the moles of gaseous product minus the moles of gaseous reactant. This equation is given to you on your yellow equation sheet. If you are given a K sub C and they want to know what would it be in terms of pressures, you can interconvert them, or vice versa. The equilibrium constant can be, or the equilibrium of a reaction can be reached from either direction. As you can see, the ratios of NO2 to N2O4 remain constant at this temperature no matter what the initial concentrations of N2 and N2O4 are. You can see the equilibrium constant right here is pretty much constant no matter what the equilibrium concentrations were, or the initial concentrations were to start with. Eventually, when equilibrium is reached, the constant is the same. This is the data from the last two trials from the table on the previous slide, experiment 3 and experiment 4. Notice how the concentration of NO2 ends up the same no matter whether you started with 0.04 or with 0 molar of that concentration. It does not matter whether we start, here's a second example reaction. This is N2 plus 3H2 goes to 2NH3. It does not matter whether we start with N2 and H or whether we start with NH3. We'll end up having the same proportions of all three substances at equilibrium. So what does the value of K mean? If K is really big, that means the reaction is product favored, then there's more products than reactants. If K is less than 1, the reaction is reactant favors, and the reactants predominate at equilibrium. So how can we use the equilibrium constant? The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant in the forward reaction. So if you look, N2O4 goes to 2NO2. If we look at the reverse of that, it's simply the upside down of this fraction. So if you flip a reaction around, all you have to do is take the inverse, or the reciprocal, of the equilibrium constant. The equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. So notice if we take this equation and multiply it by 2, now this 2 and 4 become exponents in the same equation for the equilibrium constant. You notice this one is a 2 and a 1, this is a 4 and a 2, which means what I did was squared the equilibrium constant. The equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. That means you multiply them together. Next we move on to heterogeneous equilibrium. This means when there's more than one phase of matter present. The concentration of solids and pure liquids are essentially constant, and both can be obtained by dividing the density of the substance by its molar mass, and both of these are constants at constant temperature. Therefore, the concentrations of solids and liquids do not appear in the equilibrium expression. Notice in this chemical equation showing lead chloride dissolving in water, lead chloride solid does not appear as the reactant, Pb plus 2 and Cl minus squared, is not divided by PbCl2. We always say it's products divided by reactants to the power of its coefficients. Well, in this case, we don't divide by the reactant because the reactant is a pure solid or a pure liquid. They, meaning pure solids and pure liquids, never appear in the equilibrium constant expression. As long as some of the calcium carbonate or calcium oxide solid remain in the system, the amount of CO2 above the solid will remain the same. Notice here they have some calcium oxide, some calcium carbonate in here. Notice as long as some of the solid remains, this gaseous amount of CO2 will remain constant. And so the equilibrium constant expression would only be based on CO2 gas for this equation, because these two solids would be left out. So let's look numerically and mathematically at equilibrium calculations. We'll do a number more of these and step-by-step examples in the next video cast. Here's an example problem where we have a certain amount of hydrogen and a certain amount of iodine. This system is allowed to reach equilibrium, and analysis shows that the concentration of HI is 1.87 times 10 to the negative third. Calculate K sub C for the reaction. Here's the reaction. Our first step is to make a table of what we know about hydrogen, iodine, and hydrogen iodide. These were the initial amounts of hydrogen and of iodine, and we had no hydrogen iodide to start with. Notice this takes on the form of an ICE table, or an ICE table. This is how much hydrogen iodide we had at the end of the reaction, or at equilibrium. So this increases by 1.87 times 10 to the negative third, and therefore these decrease at half the amount, because remember the ratio was 2 for every HI for every 1 I2 and H2 from the balanced chemical equation. Doing some subtraction, this is the amount that we have at equilibrium for H2 and I2. You can now plug these values into the equilibrium constant expression and solve for the equilibrium constant itself. Notice the constant expression is products to the power of its coefficient divided by each reactant. The reaction quotient, Q, is very similar to the equilibrium constant itself, except one substitutes the initial concentrations on reactants and products into the equilibrium expression. Q gives the same ratio the equilibrium expression gives, but for a system that is not at equilibrium. That's why it's called the reaction quotient, and is symbolized by a capital Q, and is not called the reaction equilibrium constant, because it's not at equilibrium. If Q is equal to K, the system is at equilibrium. If Q is greater than K, that means there is too much product, and the equilibrium will shift to the left. If Q is less than K, there's too much reactant, and the equilibrium shifts to the right to form more products. By calculating Q, you can determine which way the reaction will shift or move to obtain equilibrium. Lastly, the chapter talks about something called Le Chatelier's principle. Le Chatelier's principle states that if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. The types of disturbances we'll talk about in illustrating Le Chatelier's principle we'll use what's called the Haber process, or the Haber process, which is the production of ammonia from nitrogen and from hydrogen. Notice there's one nitrogen molecule and 3 hydrogen molecules coming together to make 2 ammonia molecules. If H2 is added to the system, N2 will be consumed, and the 2 reagents will form more NH3. So if we increase the concentration, or the amount of H2, we'll shift to the reaction to the right. In this process, this apparatus helps push the equilibrium to the right by removing the ammonia from the system as a liquid. So if you look back at this reaction, if you remove some ammonia or decrease the concentration here, the reaction will shift to the right to replace it. Pressure can also affect equilibrium, and we'll look at that in the next video cast, how pressure has a huge effect on the change in equilibrium, and therefore volume as well, since pressure and volume are inversely related. And lastly, temperature can affect a change in equilibrium as well, depending on whether the reaction is endothermic or exothermic. Catalysts simply increase the rate of both the forward and the reverse reactions. They do not change the equilibrium constant. Remember, once you reach the equilibrium amount, the amount does not change. A catalyst, though, does offer an alternative pathway that is quicker and therefore will increase the rate of a reaction. Equilibrium is achieved much faster, but the equilibrium concentration and composition remains unaltered.